All right, so today we're going to be talking more about enolate chemistry and using enolates as nucleophiles for alkylation and also multi-step synthesis. But in order to do one of our learning objectives today, we really got to remember this decarboxylation reaction that you learned in chapter 19. And so if you remember, if you have a carbonyl beta to a carboxylic acid, so remember alpha, beta. So if you have a carbonyl beta to a carboxylic acid, we can draw these kind of cyclic arrows like so to do decarboxylation, which means loss of CO2, in order to lose a carbon from our molecule. And so we are going to use that reaction in a multi-step synthesis today. It's a very common sort of sequence of events to do multi-step synthesis. So I just wanted to remind you that you have learned that reaction and we're going to use it today. We also need to remember E2 and SN2, which you learned in 2301, right? In particular, the reaction we're learning today is an SN2 reaction. We've obviously used that, that mechanism a lot in this class, but now we're going to use it in the context of enolates. All right, so our two learning objectives for today is the 4 Ps of enolate alkylation, so that is an SN2 reaction, and then planning a multi-step synthesis using some of these enolate reactions. So let's start with our first learning objective of the day, the 4 Ps of enolate alkylation, which is section 21.5 in the book. So just like every other reaction in this chapter, right? The chapter is essentially enolates as nucleophiles. So you guessed it, we're going to use an enolate as a nucleophile. So we're going to have our, say, ketone in this case, could also be an ester. We're going to use a base. So if you're using like a single ketone, you're going to use LDA. Remember that very, very strong base that we talked about earlier this week, which is going to form our enolate fully. And then once we have an enolate, we can do an SN2 reaction in a second step with some sort of alkyl halide. So this is our electrophile in this reaction, so that we can alkylate or add in that alkyl chain to our nucleophile. So here my electrophile had 1, 2, 3 carbons, and I added in 1, 2, 3 carbons. So this is our overall reaction. I'll walk through the mechanism in a bit, but it's just an SN2 reaction. This last step is just an SN2 reaction, just like every other SN2 reaction we have learned previously. But before I get there, this is actually not the way we normally do this. You can do it, but there are some problems. If you just have a single ketone, there are some problems. So let's talk through the problems. First of all, if using a single carbonyl enolate, you can only use primary alkyl halides. So the one that I drew up here, right? If we look at this carbon right there, that is a primary alkyl halide, right? Because it has 1 carbon, the leaving group, and 2 hydrogens on it. So only primary alkyl halides. And the reason for that is because secondary and tertiary alkyl halides will undergo E2 elimination instead of SN2. So that would be the case where the enolate acts as a base instead of a nucleophile. So remember that SN2 and E2 can happen under the same conditions. It's just whether your reagent is acting as a nucleophile or a base. So let's show an example of that. So if I draw my enolate, in addition to this enolate being nucleophilic, it is also basic. And so if I have an electrophile that is a little bit bulkier, right? So a secondary electrophile, so it's slower to do SN2. So let's show this, for example. So this would be our electrophilic site that is secondary, right? So the SN2 reaction is slowed down, right? Slowed down. And so in the meantime, this is also a basic enolate. So instead of doing the SN2, it's going to do E2. And so what that looks like, our lone pair pushes down. Our CC double bond is going to grab the proton instead of attacking as a nucleophile. And then we do E2 elimination. Remember, E2 elimination is done in a single step. And that ends up with a proton in that alpha position plus this alkene, which is your elimination product, plus lithium bromide is the byproduct. Okay, so this is undesired. We don't want this to happen, but this is the other alternative if you're using an electrophile that's not very fast for SN2. Okay, so that's the first problem. That if you only have a single, carbonyl, that enolate is also very basic in addition to being very nucleophilic. So that's the first problem. The second problem is a problem of selectivity. So if you have an unsymmetrical ketone, you can get a mixture of products. So let's look at an example of that. So say we have this ketone, right? It's unsymmetrical because one side has that additional methyl group, the other side does not. So we have two different alpha protons. So if we were to do this reaction, LDA, second step, some alkyl halide, like this, we would get two different products. We could alkylate on the left side. 1, 2, 3. 1, 2, 3. Or we could alkylate on the right side. 1, 2, 3. So and the reason that we do this, or we could that this happens, is because we can form two different enolates. So if we just break down that first step, we could form an enolate on each side. This plus this one. So we get two different enolates. Now these enolates are different. So sometimes you will have a major product and a minor product, but you generally do get mixtures that can be difficult to separate. And so this gets really challenging. So even when both of these can go on to do the second step, you're going to get these mixtures of products and they're going to be hard to separate. So we often don't do this reaction using a single carbonyl. We usually are going to use those beta-dicarbonyls that help with both of these problems. Okay, so you can do this. It's just a little bit less common. It is more common to use these beta-dicarbonyl derivatives. Okay, so let's show an example of the beta-dicarbonyl and why it solves both of these two problems when doing enolate alkylation. So let's remind ourselves of what beta-dicarbonyls are. So we talked about this a week ago when we were introducing enolates, right? We can have two ketones. We could have one ketone and one ester, for example, or we could have two esters. Like so. And we talked about how the alpha protons in the middle of the two carbonyls are going to be much more acidic than if it was only by one. So just as a reminder, our pKa's of these were 9 for the diketone, about 11 for one ketone, one ester, and about 13 for the diester. Okay, so much more acidic protons. So that means it's going to be easier to deprotonate, right? So when we do this reaction, in our first step, when we use a base, we can use LDA if we want, but because these are more acidic, we could also use a slightly weaker base like that sodium ethoxide, where again, we want our alkoxide to match our ester so we don't get mixtures. Okay. So either of those two bases work because we have more acidic protons now. And then we can do our second step with our alkyl halide. Okay, so why does this solve our two problems? Well, when you have two carbonyls that are beta to each other, it's only going to alkylate in between the two. Because that is the most acidic proton. That means that it is regioselective. Regioselective, right? Because it's always going to go to that center position. The other thing that it helps with is that the enolate is less basic, such that both primary and secondary alkyl halides work. So it's less basic, therefore E2 elimination is less likely to happen. But tertiary alkyl halides still undergo E2. So it's not perfect, right? But it's better. We can use primary and secondary. All right, so let's just show an example. Okay, so here we have that beta-dicarbonyl. We've got that central alpha proton. First step, I'm going to use my sodium ethoxide, checking that my alkoxide matches my ester. Second step, I'm going to use a secondary alkyl halide. And I'm going to add 1, 2, 3, 4, 5 carbons. Okay, so I'm going to draw my beta-dicarbonyl again, so, and then I'm going to attach my alpha position. Oops, just keep my color coding the same. I'm going to attach my alpha position here to that 2 carbon. So 1, 2, 3, 4, 5. Okay. So you just have to identify our nucleophilic site, which is always our alpha carbon, right, of the enolate. And it's going to do an SN2 reaction with our alkyl halide to form a new carbon-carbon bond. So let's explicitly draw out that mechanism. Which is basically 2 steps. So first, we need to make our enolate or make our nucleophile, just like every other reaction in this chapter. So step 1, we have our base. Draw out my lone pairs this time. Our base is going to grab that proton, generate our enolate. So now we have made our nucleophile, right? Made our nucleophile, which is our enolate. And so we are now ready to do our SN2 reaction. So our second step, we're going to introduce 1, 2, 3, 4, 5, our alkyl halide. Again, that's our electrophilic site, carbon attached to the leaving group. We're going to do an SN2 reaction. So remember, this is the weird arrow pushing for enolate nucleophiles. Lone pair pushes down to reform the carbonyl. CC double bond attacks our electrophile, leaving group leaves. SN2 mechanism. The ester part of the molecule didn't change, so we're going to keep that the same. And then we're going to count our carbons. 2, 3, 4, 5. 1, 2, 3, 4, 5. Questions on that? Yeah. Yeah, great question. I could have drawn it either way because there is a resonance structure of this enolate that is on the other side as well, right? I drew it into the ketone because technically the ketone is a little bit more withdrawing, but it doesn't matter. Both of them are the same. But that's a great question. Yeah, you can draw it either way. You have resonance structures, that's going to be both. Yep, great question. Other questions? Yeah. Yes, that's a great question. Okay, so we're going to get there in a second. But yes, there is another alpha proton here. So you could do this again. But remember that we're doing this stepwise, right? So in the first step, we're fully forming the enolate. So it's sitting there, right? And then we are adding in our electrophile in the second step, right? And so we're not actually regenerating our base. We're generating a salt. But you're onto something there. We're gonna talk about that in a little bit. Yeah. Yep, absolutely. Yep. So if I draw in the byproduct here, right, we have a sodium counter ion. So we have sodium plus and we have I minus. Yeah, so it just forms a salt at the end. Great question. Yeah. It's a good question. I think it is, in this case, it's both, right? Because we're not differentiating between kinetic and thermodynamic, but because I don't think that if you leave it longer, it's going to change into something else. So in this case, there's no difference between the kinetic and thermodynamic product. It's just that this is the only pathway that it can really do, unless it were like be able to do the E2, for example, right? But you don't convert one into the other if you leave it longer. So in this case, that doesn't really have a differentiation, I would say. Okay, let's do a timing question to see if this is making sense. Okay, predict the product of the following reaction. So you're given this diester in this case, and then you're given some reagents. I would like you to tell me what the product is going to be. So again, make sure we count our carbons. Think about what's going to happen. Feel free to chat with your neighbors. See if they're getting the same answer as you. above. This is our electrophile, so I'm going to add in that electrophile like so. I'm going to do my alkylation. One, two, three, four. Okay, so I added in my extra carbons, right? I kind of built up my carbon skeleton. Now I can do my saponification. With my acidic workup to get to my diacid. Still alkylated. And now I'm ready to do my decarboxylation. Lose one of these carboxylic acids as CO2. And we finally get to our desired product. Okay. So this is a really common sort of sequence of reactions that's sometimes called malonic ester synthesis, because this is a malonic ester, which is the ester form of malonic acid. But so sometimes you'll see it called malonic ester synthesis because it starts with malonic esters. Okay, questions on that? We're just going to do a bunch of examples, but does that concept make sense? Okay. So when it's a carboxylic acid, I think it's a little bit more clear where that cut should be. I think it gets a little bit more complicated when it's a ketone. So let's look at an example where it's a ketone. So you're asked to make this from an alkylation reaction. So we can think about, there are two possibilities because this ketone has two alpha positions. So we could have alkylated on this side, or we could have alkylated on this side. Again, I'm drawing the cuts after the alpha position. Make sure we do that. So let's see which one makes the most sense. It's okay if you don't know at the beginning, we're going to figure it out. So let's do the red one. So what would the red one need? I would need the left side of the molecule to be my enolate. Okay, I'm going to put that in quotes again, because we don't know if that nucleophile exists yet. And then I would need my right side of the molecule to be my electrophile. Anybody see any problems with that? Just like any other SN2 reaction we've learned all semester, that is an sp2 carbon. We cannot do SN2 reactions at sp2 carbons. Right? This has come up a couple of times this semester, so just reminding yourselves of the rules, right? So we cannot do SN2 at sp2 carbons. Cannot. Not possible. Therefore, that is not going to be the way that we do this. So we have to do it on the other side. Okay, so what does that give us? We cut it on the other side. 1, 2, 3. We can look at this. That is a primary alkyl halide. That's good. Right? It also would not be good if it was tertiary, but primary and secondary can both be fine. And then we would need an enolate that looks like this. Okay. An enolate that looks like this. So then we ask ourselves, does this enolate exist? Or could I make this enolate? So if I went back one step from there, the ketone that would come from would look like this. The problem is that I have alpha protons on both sides of this ketone, right? So two different alpha protons, which means that we're going to form two different enolates, and it's going to be kind of problematic. So we don't want to do it that way. So instead, this is where having that dicarbonyl, right, helps with the regioselectivity. So we're going to want our ketone part, and then we need to add in the beta-carbonyl, and it better be an ester if we want to get rid of it later. Okay, so that's the logic. That's how I think it through, step by step by step. It's okay if you don't know at the beginning, draw out what it would be, and then ask yourself in the forward direction. I think it's a lot easier to think in the forward direction. So taking one step back and then being like, okay, would I be able to go forward? If yes, go one more step back, right? I think that's a little bit easier. So challenge to you is to draw this one in the forward direction with all the conditions. So I will post the answer to that with my notes. Okay, but that's kind of the logic of how to think it through step by step by step. All right, let's do one more. If you were asked to make something like this. Okay. So our ketone here has this alpha position, so I can cut here. So if we go backwards one step, this part would be our electrophile. So say an iodine this time. Okay, and then what would our nucleophile need to be? Would need to be this enolate. So then we ask ourselves, could we go forward from this position? What type of alkyl halide is this? Primary, secondary, tertiary? What do we think? Seen some twos? Yes, this is a secondary alkyl halide. Remember, there's one hydrogen here as well. Secondary. Can we do an alkylation from a single carbonyl enolate on a secondary alkyl halide? No, we cannot. So if this were to react, it's going to be doing an E2. So this is too basic. So it's going to do an E2 elimination with a secondary alkyl halide. So again, we cannot just use this as the starting material. We have to kind of go back an additional step to make it less basic. So how do we do that? Again, we need that beta carbonyl derivative. So here we have that ketone. Here's our alpha position that we need to make less basic. So attached to that alpha position, we need to add that ester that allows us to remove it later. So I think that this is challenging because when you're looking at the product that you're trying to make, it actually has one fewer carbon, right, than what you started with, because we're doing this decarboxylation. So I think that this is why this is a very tricky series of reactions. But if you take it step by step and then you think about it then in the forward direction, it's clear that you can't just use the ketone by itself because it will do E2. So then you have to add in sort of this extra ester group right, that you can then remove later. Questions on that? Yeah. Yeah, that's a good question. So if you were to cut this one, so that's harder because that's forming a ring, right? And so those two things would still be attached to each other, which is just more challenging synthetically. Whereas this comes from like a much more symmetrical molecule that is easier to think about how you would make a single enolate from that. Because over here, you'd have two potential enolates to make. Does that make sense? You can draw it back. So if I go here, what would that look like? One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. And then you'd need your halide here. You would be able to make two different enolates from that, right? So it'd be harder to control the selectivity in that case. All right, thank you very much. That is all from me. I think we'll finish up chapter 21 on Monday.